Now we're going to look at similar right triangles that are created when you take a right triangle and you do an altitude to the hypotenuse. That means the hypotenuse is going to be the base, and you're going to have the right angle be on top, and you draw a vertical segment connecting the base, which in this case the hypotenuse, to the right angle. So we're going to prove that these triangles are always congruent. So I'm given, here's my triangle with my hypotenuse on bottom, AC, and the right angles at the top at the apex. And I've dropped a vertical segment here. This is going to be the altitude, BD. Okay, we're going to prove that BDC is actually proportional to ADB. How are we going to do that? First of all, we know that all right angles are congruent. So I have one marked with the blue here. There's another one. I put that one in just to make it a little easier and clearer to see. So BDC, that's this right angle right here, is congruent to CBA, the original right angle that's at the top of the big triangle. And that's also congruent to BDA, where I drew in that blue right angle. Next, I can say that this angle is congruent to itself. Angle A is congruent to itself by the reflexive property of congruence. You're probably saying, well, that's only one angle. But that angle is in two different triangles. It's in the large triangle that's yellow here, triangle ABC, but it's also in this smaller blue triangle. So since the smaller blue triangle has a right angle in angle A, and the large triangle has a right angle on top in angle A, both of these triangles are similar by angle-angle similarity. I'm going to do the same thing on the other side. Angle C is congruent to itself by the reflexive property of congruence. And basically the same thing. Now I'm going to look at this inside triangle. They both have an angle C and they both have a right angle. So the large yellow triangle and the red triangle inside are both similar to each other by angle-angle similarity. Now there are two ways I can say that the red and the blue triangles are similar. One, I could just do it by angle-angle because they both have, well, I haven't really shown that those two angles are congruent. Probably the easier thing to say is it's really the substitution property of equality, or it's really the transitive property. It would be better. I would actually scratch this off. It's a transitive property because, so scribble through that, right, transitive. If ABC is similar to ADB and ABC is similar to BDC, then all three triangles have to be similar. So it's sort of that chain relationship. Now, how do we set up proportions for these? Draw the triangles separately in the same orientation. These will probably be the hardest similarity problems we give you. So you really want to take the time to draw all three triangles separately. Write a similarity statement with the matching vertices. So if you have to, color code your vertices in the three separate triangles. It's going to be very difficult if you try to do it all in that one picture. You'll probably get it wrong. Then color the corresponding sides so they match and set up the proportions. So I like the corresponding sides. I do like doing the color coding. On this example, I did not. As long as you have them in the same orientation, you don't have to color code. But it doesn't hurt to color code, and if you don't keep them in the same orientation, you really need the color. So in this example, I'm going to write the similarity statement. So the first thing I do is draw three triplets, really, because I've got three different triangles. And I'm going to go ahead and put in the right angles. Ignore the red mark for the moment. Then I'm going to put in all of the angles that match angle T here. All right. So all three of these are going to have an angle that's congruent to T. And then they're all going to have an angle that's congruent to angle S. Start with the big one that's the same orientation. So TRS. That's pretty easy to fill in. Then I'm going to take the triangle on the left. All right. The right angle on the triangle on the left is actually up here at U. And the 2 angle mark is T. So I can put T there and U down here. The only other point left on this triangle is R, so I fill that in. Okay, let's do the same thing with the triangle on the right. So I fill in R because that one is going to be my double angle. You might not see that right away, so pretend I didn't put the R there. The U is definitely the right angle, and the S is the same angle for both triangles. So you might not have noticed the R right away. And when I do R here, I mean URS, that angle right here. So you can see that this angle and this angle are actually the same angle. And it's always going to be that way. So, for example, if I picked 60 degrees for this large one, right, that's got to be 30. Well, I've got a right triangle up here, so if that's 30, that has to be 60. I can really only have a combination of 3 angles for this right triangle. If I already know 2 of them, I only have one choice for the third. So now that I have these all in the same order, you can see STR is going to be the same as RTU and SRU. So there's RTU and there is SRU. Now let's go ahead. Most of your problems are actually going to be doing finding missing values, like this problem right here. So we're going to do the similarity statement. I have to draw the triplets. And here I have all the angles marked. So I took this triangle and drew it 3 times. The first set of vertices is pretty easy. It's EFG, just like the triangle is. And I have 144 plus 25. That's this whole side right here. So that's 169. Okay. Now let me go ahead and do this triangle on the left, EFD. Which way does it go down here? Well, angle E is the same as angle E, so I can put that one there. On this half of the triangle, EDF is actually my right angle, so it's easier to see D, which means F goes on my last point. Then I can put in my 144 for ED, and let's go ahead and do my points for my right triangle, which has F, D, and G. Well, I know G is the same because it's exactly the same angle there. My right angle's at D, and so that means F is over here. So if I'm doing EFG, that's going to go with EDF and FDG. Oh, let me fill in my values. So it's EDF and FDG. And I took the 25 here, that's DG, that goes there. Now, this is probably one of the harder types of problems for a right triangle similarity, which is already pretty hard. And I want to find the other missing values. I want to find FD, I want to find EF, and I want to find FG. If I had had any 2 sides known on these triangles here, I could already start setting up a proportion. So I've given you the case where you only see one side on each of these triangles. So when I see these 2 parts of the segment, the important thing to notice is that segment FD is the same for both the left triangle and the right triangle. So I'm going to call that X, all right? And I put it on both triangles. Now do you see how 144 is to X as X is to 25? You're probably going, wait a second, they're 2 X's. But X is supposed to have the same value. So when I set up that relationship and cross multiply, I'm going to get X squared equals 3600. I can actually solve that. And the reason I get X squared is X times X is X squared, by the way. So I can take the square root of both sides, and I get X is 60. So now I'm going to put 60 in for FD down here and right there. Okay, so I have a couple options. I could try to do some proportions, but probably the easiest thing to do is to go ahead and use Pythagorean theorem to find EF and FG. So EF squared, and I'm using this middle triangle right here, equals 144 squared plus 60 squared. Just basically use the calculator, take the square root, and I get EF is 156. So I'll put it up there and down here. Same thing for the bottom triangle. I can use Pythagorean theorem again. F squared equals 25 squared plus 60 squared, or 625 plus 3600, 4225. Take the square root of that, and I get 65. So for further reflection, why does the altitude to the hypotenuse always create similar right triangles? And how do we set up proportions for similar right triangles? It's very important to remember that you really want to draw all 3 triangles separately. Otherwise, these can be incredibly confusing problems. And also, if you noticed a shortcut for finding the altitude when you know the segments it creates. Well, if you want to check that out, it's actually in your textbook. It's called the geometric mean, and it has to do with this proportion here and the way that you have X kind of almost matching on that cross multiply product. It's not really a match, but where they're kind of diagonal to each other. So you're always going to end up with this sort of x squared when you cross multiply, and the product of these two pieces. So feel free to check that out in the book. I'm not going to quiz you on geometric mean. It's just a cool little side note.